This is a model of how river networks evolve and change a landscape over time. It was developed by my advisor, Taylor Perrin, here at MIT, based on theory and measurements of the effect of Earth's rivers on the rocky surface of the continents. But I've been using the model to study Saturn's largest moon, Titan.
Until recently, we didn't know much about Titan's surface at all. We knew that the atmosphere was mostly nitrogen, like Earth's, and that there was also a lot of methane in the atmosphere. We knew that it was very cold, and so there was the possibility that methane might exist not just as a gas, but also as a liquid. And so it was speculated that there might even be oceans of liquid hydrocarbons on Titan's surface. But we didn't have much more information than that because Titan's very far away. And even more challenging is the fact that all of these organic molecules in the atmosphere make it very difficult to see the surface. So effectively, Titan's stratosphere is just full of smog. And the observations from Earth can't see through that smog at visible light wavelengths. So there's just a couple of windows where you can take pictures through the smog, and looking at it from very far away, there wasn't much detail about the surface at all. In addition to the difficulty of actually seeing Titan's surface and taking the images that we now have, another challenge that we have to deal with is the fact that it's a very exotic environment. And so in addition to the difference in gravity, there's a difference in atmospheric composition. And so the liquid that we're dealing with that rains out of the atmosphere, runs off of the surface, and makes rivers and cuts into the surface is methane and not water. The material that's being incised into is not rock like it is in most cases on Earth, but mostly water ice. And so it's not immediately clear that the landscape on Titan should behave like it does on Earth. And yet we see striking similarities between the landscapes that have been imaged on Titan and river networks we see here on Earth. And in fact, as long as you know what the properties of those materials are, and you use the right kind of theory that takes that into account, you can study the mechanics of hydrocarbon rivers cutting into ice just like you can rivers of water cutting into rock.
The problems Taylor described in actually seeing what the surface of Titan looks like were partially solved by the Cassini spacecraft, which entered into orbit around Saturn on June 30th, 2004. It doesn't orbit Titan, but it flies by Titan every once in a while, and every time it does a drive-by, you get a single image of a piece of the surface created by the synthetic aperture radar instrument on board. It's not a normal picture like the satellite images in Google Earth, but rather a radar image. The radar can penetrate the haze. The radar pictures are the highest resolution view we have of large areas of Titan's surface. They're still kind of coarse, about 300 meters per pixel at best, but that's what lets us see the drainage networks, and they're what I've been using to study how rivers on Titan have modified its surface. Here are radar images taken by Cassini. They reveal bright and dark features that stretch for hundreds of kilometers in some cases across Titan's surface. This is one of the images I worked with. The dark Rorschach blobs are liquid hydrocarbon lakes near Titan's North Pole. Cassini has captured images of sunlight glinting off the flat surface of a lake, which is one of the ways we know that the lakes really are full of liquids. The largest of the lakes in this image is called Ligeia Mare, named after one of the sirens in Homer's Odyssey. The white lines are valleys cut by rivers of methane that I identified and measured. The longest river network in this image is about 200 kilometers long, though you can also see dozens of smaller networks. In this radar swath, which is 100 kilometers across, you can see some of the most distinct groups of river valleys at the opposite pole, at around 75 degrees south. One of the valleys appears to meander, similar to how some rivers on Earth meander. This image hints at a diverse landscape. Other studies have shown that Titan is home to mountains, which can reach 2 kilometers in height, and vast deserts filled with dunes. In our study, we compared the shapes of river networks on Titan and Earth to the river networks in our model. On the left, you can see a detail from one of the radar images of Titan's surface, and on the right, a snapshot from the model. We found that many of Titan's river networks are relatively elongated and spindly, which suggests that in some regions of Titan, the hydrocarbon rivers have produced surprisingly little erosion. Based on these results, we conclude that either erosion on Titan is much slower than on Earth, or Titan's surface has recently been renewed, perhaps by a process such as the eruption of icy lavas or by tectonic upheavals. We have a lot more to learn about Titan, and what we're learning could help us answer some fundamentally cool questions about Titan's history. Titan is one of the very few places, besides Earth, where we found active modification of the surface by flowing liquids, and we're excited to learn more about this familiar process on an entirely different world.